All right, we got a toy train. The mass of the toy train, make sure you put that in kilograms. You always want your mass in kilograms. 0.875 kilograms. Okay, the train starts from rest, and in a time of 21 milliseconds, you want that to be in seconds, 0.021 seconds. V final is 0.62 meter per second, and what they want us to find is the power delivered to the train. So like, you could look at power two ways. The two ways to look at power, you could say power is the work done by the train per time, or power equals the energy used by the train per time. But either way, what do we measure work in? Joules. What do we measure time in? Seconds. What do we measure energy in? Joules. So either way, this is going to be in joules per second. So I'm going to show you both ways to do this. Work per time and energy per time. So let's start with work per time. There's a few things we're going to need that we got to calculate ahead of time. So for example, how far does the train travel from start to end? With the ending being when it has a velocity of 0.62. What's the displacement in between those 2 points? Well, we can use a kinematic. X equals 1/2 VF plus V initial times T. V initial is 0. So you solve this for displacement and you get 0.0065 meters, 6.5 millimeters. 0.0065 meters. That's how far it travels. The other thing we're going to need is the acceleration. The acceleration of the train. So we can do a kinematic. We could go VF equals V initial plus AT. V initial is 0, so A is V final over T. So just divide 0.62 by 0.021, and we get an acceleration of 29.52 meter per second squared. Okay, so let's do power equals work over time. So we're looking for the power of the train, right? Power of the train, so that's going to be work of the train. What's the basic work equation? Force times displacement, that's going to be the force of the train, the force of the engine over time. So do we know the displacement? Yes. It's 0.0065. Do we know the time? Yes. What's the thing remaining? To find the force of the train. Well, hey, if friction is not mentioned, does this problem mention friction at all? No. The rule is, if friction is not mentioned, we assume what? It's not there. There's no friction. So here's the train. I'm going to draw. Here's the little train right here. So what's the only force in the x direction? It's the force of the engine, or we'll just say the force of the train. T for the train engine. And then we have mg down, which is not going to matter, and then normal force up, which is it's not going to matter, because we're trying to find the force of the train. So when you sum the forces, the only force in the x direction is what? The force of the train, so that's going to equal ma. So the force of the train engine, so the mass is 0.875. The acceleration is 29.5 meter per second squared. So we find out that the force of the train engine is 25.83 newtons. Okay, so we plug that in up here. So I'm going to plug into this equation right here. So the force of the train engine is 25.83 newtons. The displacement that the force acts. Hey man, is the force parallel to the displacement? Whenever you use the work equation, force and displacement have to be parallel. Is the force of the train parallel to the displacement? Yeah, so we're good. All right, the displacement was 0.0065 meters, and that all took place in a time of 0.021 seconds. You punch into that, and you're going to find out that the power of the train is 8 watts. Okay? Now, Another way you could have done this, and I think you'll like this next way better, the other way you could have done is what? What's the other way to look at power? Energy per time. And this is particularly nice because there's no friction. If friction's present, you got to factor that in, because what is friction doing? Sucking energy up. So it's like the train is working against it. But here there's no friction. So what we're going to say? We're going to say the power of the train is going to equal the energy gained by the train over time. All right? What's the only energy that this train gains? Kinetic. Now, if it were going up a hill, it would be gaining potential of gravity, right? But here it's on a flat surface, so the only energy gained by the train is the kinetic. So look, you're just going to go, okay, power of the train, kinetic energy is 1/2 mv squared over the time. So that's 1/2 times 0.875 kilograms. V final is 0.62, and then square that, and then the time is 0.021 seconds. The power of the train, again, 8 watts. So you could do it that way too. Okay?